Okay, honors physics. So on Friday of this week, you're going to have a little bit of a more involved quiz than you did last week with rotation. And it is going to include everything we learned about rotation. So essentially, there were three kind of distinct parts of rotation that I taught you, and some of them are linked and some of them are not. So the three things we focused on are uniform circular motion, rotational kinematics, and then torque. So I just wanted to kind of summarize all of that. I'm not teaching anything new here. This is all stuff that you should have in your notes already. But I want to make sure that you understand how these concepts are linked, and maybe when is appropriate to use what kinds of things. And we'll sort of keep a running tally of our equations over here on this side of the board. So uniform circular motion is where we started. And we start here because it is the simplest type of rotational motion. You see me often in the notes, I was calling it UCM. And so when something is in uniform circular motion, that means that it is rotating with a constant radius, a constant speed, and a constant acceleration, which is centripetal only. So you have three things that are constant. You have a constant speed. Now your velocity is always changing because your direction is changing, but your rate of rotation stays the same. So you have a constant speed, you have a constant radius, and you have a constant centripetal acceleration. You have no angular acceleration in this kind of motion. So the rate of rotation is not changing. That's the point for uniform circular motion. And so when we did uniform circular motion problems, this is where we were spinning, and back when I had you in class still, in a classroom, spinning the thing over your head at a hopefully constant rate. We did problems with a roller coaster moving at an assuming constant rate. We did problems where you had the astronaut in a centrifuge spinning. We looked at something vertically spinning. So those are the kinds of things we can do with uniform circular motion. And when we had uniform circular motion, there were three equations that you were using. One was that the centripetal acceleration is equal to v squared over r. Now, this equation, so this is for that centripetal acceleration, which is towards the center. That equation is true actually for all rotational motion. So we use uniform circular motion to introduce it because actually it's derived from this kind of motion. I didn't do the derivation for you. But this equation is true for all rotational motion. So even if something is rotating in a non-uniform way, it still would have this centripetal acceleration. It would be changing possibly, but you could find it at any given point by taking v squared divided by r. The second equation that we used was that the velocity of this thing spinning was its circumference divided by period, the time it takes to go around the circumference. So that's an equation that's used for uniform circular motion. And the third thing was that the sum of all forces is equal to ma, which is mv squared over r. In this case, again, we can only really use that for uniform circular motion. So a lot of the work we did in chapter 5 dealt with uniform circular motion. Now we moved from the beginning part of chapter 5 into chapter 8, and in chapter 8 we started to look at what we call rotational kinematics. And rotational kinematics can be used when something is experiencing uniform circular motion or when it's experiencing non-uniform circular motion. So when we get into that rotational kinematics, it's true for all rotation, uniform or non-uniform. And so rotational kinematics introduced us to some new variables. So we said that displacement, which we are used to in linear form saying like x minus x naught, right, or y minus y naught. In angular form, we use theta minus theta naught. Change in theta will give us our displacement. And we can measure that in degrees, radians, revolutions, rotations. We generally prefer radians here. But there's all sorts of units you can measure displacement with, just like in linear form, right? I can measure displacement in centimeters, meters, inches, miles, etc. Velocity. For linear motion, we say that velocity, average velocity, is displacement divided by time, right? It's the rate at which motion occurs. In linear form, we use a new symbol, Greek letter omega, and average velocity is angular displacement divided by time. And then the final thing is I introduced a new kind of acceleration. This is an acceleration that is different from centripetal. So again, this acceleration is always there. So v squared over r. The angular acceleration is alpha. And actually, let me erase this and say, so in linear form, acceleration is change in velocity divided by time, right? So the angular acceleration is alpha, and it is equal to change in angular velocity divided by time. So we like that angular velocity. Usually we prefer it in radians per second, and then down here, radians per second squared. This kind of acceleration is present only in non-uniform circular motion. So you can be talking about displacement as theta minus theta naught. You can be talking about angular velocity with rotation, whether it's uniform or non-uniform. But this last quantity, the angular acceleration, is only present for non-uniform motion, because if you have an angular acceleration, conceptually what's happening is your rate of rotation is speeding up or slowing down. And if your rate of rotation is speeding up or slowing down, your speed is changing. And so you no longer have uniform motion. So these were our quantities. Again, if we're kind of keeping a tally over here, we can say like average angular velocity is angular displacement divided by time. We can say angular acceleration is change in angular velocity divided by time. And then what we can do is use these quantities to come up with kinematic equations of motion. So when something is rotating, you can use kinematics to solve for, just like we did with linear. So solve for displacement or time or final velocity or initial velocity. And so those equations are, I'll write it as a 6 separate equation, but it's really just a rearrangement of this one. So omega is equal to omega naught plus alpha t, and then theta minus theta naught is equal to omega naught t plus 1/2 alpha t squared, and omega squared is equal to omega naught squared plus 2a. I'm getting into habit. 2 alpha, sorry, times theta minus theta naught. So they look just like the kinematic equations of motion in linear form. We're just now using those angular quantities. And then the final thing when we were talking about rotational kinematics is that there's always this link between the linear quantity and the angular quantity. And I spent a little while talking about that. So if something is going around in a circle, I can say it's going however many revolutions or radians or degrees per second, but I can also say it's still going like, let's say 2 meters every second or whatever it is. And so sometimes it is helpful to kind of go back and forth between the linear and the rotational quantities. And we talked about, there's times when the rotational stays constant, like a merry-go-round. Wherever you're at on the merry-go-round, your rotational velocity, for instance, would be the same because the whole thing's moving as a rigid body around in a circle. But the linear quantity would be different. If you're close to the center, you're going a smaller displacement in linear form than if you're all the way out at the edge. And so that relationship is, we get it by multiplying by r. So I'll write it as a 9th equation. Let's say, linear velocity is equal to angular velocity times r. We say the linear, now I'm writing this with a t. The linear acceleration is equal to the angular times r. Sorry, I said t and then I wrote it. And we can even say it for displacement. Linear displacement is equal to angular times r. Now, this t here, what does that mean? This velocity, or this acceleration is not the same as centripetal. Again, that centripetal is always there, no matter what, pointing towards the center. This is a tangential acceleration. This would be tangent to the circle because it's causing the rotation to speed up or slow down. If you have questions about that, because that can be a confusing topic, maybe we'll talk through it together in our class on Wednesday. So let me know if that's not making sense to you. And then the final thing that we did with all rotations, there's a lot of equations all over the place here. The final thing we talked about was torque. And you can end up doing a lot with torque. We didn't. We just really talked about what it was. Torque is equal to force perpendicular times R. So torque is sort of like the angular version of force. Torques cause angular acceleration, so I gave you the example of the door as a classic there. And so when we apply a force perpendicular to a surface or a plane at some distance r from an axis of rotation, that force will produce what we call a torque. And then again, I didn't describe mathematically how torques produce accelerations, but I think you can picture it, right? If I push on the door handle of a door, I'm causing it to spin around the hinge. So we did just a little bit of work with torque, and you had some practice problems that you did for the end of last week with that. So again, it looks like a ton of equations, but a lot of this is really just a repeat of what you've spent months doing with linear motion. So, you know, this is like using F equals ma. We should be familiar with that. This is just all motion stuff repeated, basic motion stuff repeated in angular form. So the only really new concepts we have here are the centripetal acceleration. That's not something we've seen before we get into rotation. And then torque is a totally new thing. So in a nutshell, this is rotation. You should be comfortable doing problems with uniform circular motion. How do you know if it's uniform? I would say an object is rotating uniformly or with constant speed and radius. So the words would be there for you to know. So you should be familiar with solving problems with uniform circular motion, solving problems with rotational kinematics, and then solving problems with some basic torque. So like the seesaw problem you did in the homework.